Hello everyone, today we'll be going over this problem shown below, and this problem asks us to determine the tension in cable AB, and we can neglect the weight of the beam. So cable AB is shown here. So notice it is the same cable connected to the beam at both ends. Okay, and at both ends this cable is under the same tension. We'll call that T. So T is what we're looking for. And it looks a little complicated at first. It looks a little scary because we have our two distributed loads on the bottom here. We have a rectangle distributed load shown here. We have a triangle distributed load shown here. And we have the two tensions of this rope or cable acting on this beam as well. But once you look at it and once you get started, you will find that only one equation is needed to solve this actually. So going forward, the first step to solving this problem would be to sum up our distributed loads into a single point force. Right? So we'll break this into two distributed loads. We'll do our rectangle, and then we will do our triangle over here. So start with a rectangle, and to find the equivalent force of a distributed load, it's simply the area of that distributed load. So the first distributed load, the area of that would be 15 feet times 800 pounds per foot, and that will give us 12,000 pounds. All right, and the units will match up because our point force should be in the units pounds, which is a force. All right, so we know the magnitude of this force, but now we need to know where, at what point, this force acts on our beam. And for a rectangle, the force acts in the middle of the rectangle, halfway. So halfway is 7.5 feet. Okay. All right. So that is our force of our rectangular distributed load. So now we can look for our equivalent force of our triangular distributed load. So again, for a triangle, it's the same thing as the rectangle. We're looking for the area of the distributed load. But our equation for area of a triangle is slightly different from that of a rectangle. So for a triangle, we have 1/2 base height squared. So our base here would be 15 feet, and our height would be 800. Okay, it's just 1/2 base times height. All right, and that answer will give us 6,000 pounds. All right, so we know the magnitude of our triangular load now. Now we need to find the direction. So in class, I'm sure you found that when you find the sum of a triangular distributed load, it acts 1/3 of the way from the larger end of the triangle. So that would be 5 feet here. 5 is 1/3 of the total length of the base of the triangle, which is 15. Okay, so now we have our 2-point forces, and we still have our tension. So now we could start with our equation. And like I said before, we only need one equation in order to solve this. And that equation will be a sum of moments equation about point C. And we choose point C so we do not have to take into account the reaction forces at point C. So what I mean by that, we don't have to solve for Cx or Cy for this problem. So it saves us a few steps here. let's get back over. Okay, there we go. So we will write out our equation here. The sum of moments. So the sum of moments, we will take into account each force that is exerted on this beam. Okay, and a moment is simply a force times the radius, or in this case the length, that the force acts from our pivot point, or point C. Okay, and on top of that, we're looking for only the perpendicular component of that force. Okay, so normally this would not need to be taken into account because forces typically would act perpendicular in these problems. But here we have our angle of our rope over here at point B, so we will have to take that into account when we get there. Okay, just a little note. Okay, so we will work our way from left to right, taking into account each force as we go. So as we go, our first force will be this force here, and that is acting in the clockwise direction. So we will say that is a negative moment. This is just for convention's sake. We will say clockwise is negative, counterclockwise is positive. Okay, as long as you're consistent, you'll get the same answer, but this is how we will use it here. And like I said before, moment is force times R. So our force is 12,000, and our R, or length here, is 7.5. Alright, so that is our moment due to the rectangular distributed load. Alright, we keep working to the right now. Our next force is the tension in the rope here. Okay, so this is acting in the counterclockwise direction, so we'll make that a positive. And for this, we have tension. We defined that earlier in the problem, which is also what we're looking for. And our radius, this will act at 15 feet from our pivot point. Alright, so that's it for that tension there. Again, we keep moving to the right, and then we have our force of our triangular distributed load. Again, this acts in the clockwise direction, so we'll make that a negative. This whole thing is one equation here. I'm just ran out of space, so I'm moving down. And we said that was 6,000. And the distance it acts from the pivot point, we have our 15 plus our 5, so we got 20. Okay, and the last part of this problem, we have our tension at point B. So as I said before, we're looking for the perpendicular component of this tension. So we will say that the perpendicular component is the tension times sine of 30. But we don't want to forget our length for this this part of the equation. So when we look at it, we find our length to simply be 30 feet. Okay, and that entire equation can be summed to 0. Alright, so when you take a second to look at this equation, there is only one unknown, which makes it very nice. We have one equation and one unknown, so this can be solved fairly simply. So we'll add the two terms without a t in to the other side, and when you multiply 12,000 times 7.5 and add it to the 6,000 times 20, you're left at 210,000. That is equal to t times 15 plus t times 30 sine of 30. Okay, so scrolling down a little bit more, we can factor out a t on the right side of the equation. So 210,000 is equal to t times 15 plus 30 sine of 30. Alright, a final step here, we divide both sides by 15 plus 30 sine of 30. And we can solve for T. And when you do this, you plug it into your calculator, you are left with 7,000. And the units for tension is a force, so our units is newtons. And that's our answer. The tension of cable AB here is 7,000 newtons. Okay, so it did look a little tricky at first. Once you got started, figured out that only one equation is needed here, it was not that bad. Okay, I hope this was helpful. Thank you.